Hello everyone, welcome to this PDC lecture series. So here we will discuss about the Bode diagram of different system. So highlight of these lectures are as follows. So here we will discuss the Bode diagram of systems in series such as n liquid tanks in series or n CSTRs in series. Second, pure capacitive process. So here we will see the example of liquid tank with a pump at the outlet. So the next one is transportation lag system, and the most common example for this transportation lag system is the long pipe system. And then we will come back to feedback controller. So in feedback controller we will discuss the Bode diagram of P controller, PI controller, PD controller and PID controller. So now let's begin with the first. So first system in series. So let's assume that we have n tanks in series. So we have first tank, then second tank, and then nth tank. So for the first tank we have input Q naught, output Q1, this is small q2, and here we have small qn. So small q naught, q1, q2 and qn are the volumetric flow rate of the liquid from tank 1, tank 2 and tank n respectively. So let's assume that we have the system parameter for the first tank is tau 1 and Q1. For the second tank tau 2, K2. For the nth tank is tau n and Kn. As we already know that a liquid tank system is a first order system. So for the tank 1 the transfer function is G1 of S. For the tank 2 the transfer function is G2 of S, and the for tank n is Gn of S. So the overall transfer function for the whole system G of S can be given as per this equation, the product of I goes from tank number 1 to n G I of S, where Gi is the transfer function of ith tank. So here we can write G1 of S, G2 of S and Gn of S. So this is the transfer function for n systems in series. So to plot the Bode diagram, first we need to calculate the amplitude ratio. So the amplitude ratio will be given as the absolute value of G J omega and the phase shift will be given as the argument of capital G of J omega. So therefore substitute S equal to J omega into 1, we will have G of J omega. Let's say this is the complex number Z, and so this will be G1 of J omega, G2 of J omega and G n of J omega. So the overall expression for capital G of J omega will be the product of individual transfer function by substituting S with J omega. So using the property of complex algebra where Z equal to the product of two complex number, let's say Z1 equal to Z1 into Z2. So the mod of Z will be equal to the mod of Z1 into mod of Z2. Similarly, the argument of Z will be equal to the argument of Z1 plus the argument of Z2. So using this property, let's say this is property first. So using this property, and we also know that we can express any complex number, let's say z, in the form of polar form. So we can express z equal to mod z e to the power j, let's say 5, and 5 is the argument of z. So similarly we can express z1 as mod of z1 e to the power j 5 1. Similarly z2 equal to mod of z2 e to the power j 5 2. So therefore z will be equal to z1 into z2, and we can write this as z1 mod z2 e to the power j 5 1 plus 5 2, and which will be equal to z mod z e to the power j 5, and 5 1 plus 5 2. It means mod of z will be equal to mod of z1 plus mod of z2, and mod of z will be equal to mod of z1 into mod of z2, and so on. So for two complex number, this can be extended up to n complex number. So for n complex number, for equation number 2, so for equation number 2, using the property P1, we will get the mod of g j omega will be equal to mod of g1 mod of g2 up to mod of gn. So this will be the equation number 3, and similarly the argument of g of j omega will be equal to argument of g1 argument of g2 plus argument of gn, and this will be equation number 4. So this is equation number 4. So as we know that amplitude ratio equal to mod of G, capital G of j omega, and phi equal to argument of capital G of j omega. So now substituting the amplitude ratio in place of mod. So from 3 and 4. We can also write the equation number 3 and 4 as amplitude ratio will be equal to amplitude ratio of 1, amplitude ratio of 2, amplitude ratio of n. So this is equation number 3.1, and this is, let's say, overall phase shift phi will be equal to phi 1 plus phi 2 plus phi n. This is equation number 4.1. Taking logarithm 10 of equation 3.1. So we will get log 10 of AR will be equal to log 10 A R1 plus log 10 AR2 plus log 10 ARN. This will be the overall amplitude expression in the form of logarithm. So this is equation number 3.2. So now let's work on example. So let's say we have G1 of S equal to 1 upon 2 S plus 1, and G2 of S equal to 6 upon 5 S plus 1. So here we have two tanks whose transfer function are given as per the expression. So G1 is, so let's say the G1 is here 1 upon 2 S plus 1, and G2 is 1 upon, so G2 is 6 upon 5 S plus 1. So it means so the K1 is 1 and tau 1 is 2. K2 is 6 and tau 2 is 5. So here we have only two systems whose transfer function are given and both are connected in series. So now we have to plot the Bode diagram for two tank systems which are connected in series. So let's do that. So here we will directly apply the equation number 3.2. So the amplitude ratio for tank first system will be Q1 under root 1 plus omega square tau 1 square, and Q1 is, so here Q1 is 1 and tau 1 is 2. So here we will put 1 square root of under root of 1 plus omega square, and tau 1 is 2 square. So AR1 will be equal to 1 upon under root 1 plus 4 omega square. So this is the amplitude ratio for first system. Similarly, we can also calculate the phase shift for the first system, and that will be equal to tan inverse minus omega tau 1. So now replace tau 1 with 2. So here we will have 2 omega. Similarly, for second system, the amplitude ratio can be written as K2 upon under root 1 plus omega square tau 2 whole square, and that will be equal to 1 upon, so Q2 will be equal to 6. So this will be 6 under root 1 plus, and tau 2 is 5, so 5 square, that is 25 omega square. So this will be the expression for AR2. Now we can finally write the expression for phi 2, and that will be tan inverse minus and 5 omega. So this will be phi 2 will be tan inverse minus omega tau 2, and tau 2 is 5, so we will have tan inverse minus 5 omega. So now we will use equation 3.2. We can write log 10 of A R will be equal to log 10 AR1. So AR1 is 1 upon under root 1 plus 4 omega square. So 1 upon under root 1 plus 4 omega square, and the second one is 6 upon under root 1 plus 25 omega square. So here we will have the second term is log 10 6 upon under root 1 plus 25 omega square. So finally we can write this as log 10 in bracket 1 plus 4 omega square minus half plus log 10 6 plus log 10 1 plus 25 omega square minus half. So this can be written as log 10 AR by 6, and which will become minus half log 10 1 plus 4 omega square, and then plus log 10 1 plus 25 omega square, and this is the whole square bracket, and this is the final expression for the given two time systems. So let's say this is equation number 5. So the overall phase shift can be calculated using equation number 4.1. So we will use equation number 4.1. So we will use equation number 4.1. So here we will use equation number 4.1. So we have two tank system. So overall phase shift will be phi 1 plus phi 2, and this will be tan inverse minus 2 omega, since phi 1 is tan inverse minus 2 omega and phi 2 is tan inverse minus 5 omega. So we will put the value for phi 1, phi 2, and this will be the overall phase shift, and this is equation number 6. So now let's draw the Bode plot. Next step is to plot the gain plot and phase plot using the following equation. So here we will plot the gain plot and the phase plot using the following equation, and the first we will use the equation number 5 for the gain plot and equation number 6 for the phase plot. Now let's start with the gain plot, and here we will copy the equation number 5. So let's start with the gain plot. Gain plot. Here we will plot AR by 6 versus omega. So first we will find the low frequency asymptote. Low frequency asymptote LFA. So when omega tends to 0, we have to find the value of AR by 6 when omega tends to 0. So here we will copy the equation number 5. So equation number 5. So equation number 5 can be written as log 10 AR upon 6 equal to minus half log 10 A plus log 10 B. So we can write this as log 10 A into B. So here we will multiply both the expression. So we will get 1 into 1, that is 1, and then we will have 1 into 25 omega square and 4 into 1 square, that is 29 omega square, and next we will have 4 omega square into 25 omega square, so that is 100 omega square. So using this, we can write log 10 AR by 6 will be equal to minus half log 10 of so here omega tends to 0, omega tends to 0. So basically this is not omega square, this is omega to the power 4. So this is omega to the power 4. So omega square into omega square, we have omega to the power 4. So this is 0, and here we will have 1 plus 0 plus 0. So overall we will have minus half log 10 of 1, and that will be equal to log 10 of 1. So therefore AR by 6 will approach to 1 as omega tends to 0. So this is for the low frequency asymptote. For overall system. So next, so second step, to find the high frequency asymptote. So high frequency asymptote. High frequency asymptote. So to find the high frequency asymptote, we have to substitute omega tends to infinity, and then we will have to find out the value of AR was upon 6 when omega tends to infinity. So what will be the value of this? So again we will start with this expression. So now just copy this expression and paste so this is omega square and this is omega to the power 4. So when omega tends to infinity, so log 10, so we can take this 100 omega to the power 4 outside, and in this here we will have 1 upon 100 omega to the power 4, then 29 by 100 omega square and then plus 1. This is overall expression. So when omega tends to infinity, we will have this 1 upon, in this case we will have 1 upon omega square will be 0 and 1 upon omega to the power 4 will be 0. So substituting this value into this expression, so we will get minus half log 10 of, so this is 100 omega to the power 4, this is 4, omega plus log 10 of 100. So log 10 of 100, this will be minus half this will be 4. So this will be minus half log 10 bracket omega 4 plus log 10 100. So I can write this half 4 times log omega plus 2. After solving we will have minus 1 minus 2 log omega. This is A r upon 6 when omega tends to. This is the high frequency asymptote for the second order, for the two tank systems in series. So this is, let's say, equation number 7. So the slope of high frequency asymptote of given system equal to minus 2. So next step is find the corner frequency of individual first order system. So for the individual first order system, so omega tau 1 equal to omega, and that is equal to 1. So this will be omega C1 will be 1 upon 2 and omega C1 will be equal to 0.5. So the first corner frequency is 0.5. Similarly, for the second tank, omega tau 2, that is 5, omega equal to 1. So here omega C2 will be equal to omega, that is equal to 1 by 5. Therefore omega C2 will be equal to 0.2. So once you find the corner frequency for the individual first order system, so let's find the amplitude ratio for the given system. So we will just copy the amplitude ratio expression once again, and so here we will use this expression to find out the actual value of amplitude ratio at omega c1. So at omega c1, that is 0.5. So we will have log 10 here by 6 will be equal to minus half log 10 1 plus, and this is 1 by 2, right? This is 1 by 2. So this is 29. This is 29 1 by 2 whole square plus 100 1 by 2 to the power 4. So finally we will have 1 by 2 log 10 1 plus, and this will be 29 by 4, and this will be 2 to the 4 and 4 square, that is 16. This is 100 by 16. This is 100 by 16. So overall we will have log minus half log 10, this is 16 and this is 16 plus 4 9 ja 36, 4 2 ja 8, 8 3 11 plus 100. We will have minus half log 10, and this will be 100 . So 16 plus 16, 32, 232. So 232 divided by 16. So once we take the log of this, so we will get so here we will get log 10 of 232 upon 16 minus half. So 232 by 16 half. So 1 upon 232 by 16 to the power half. So we can write this log 10 16 upon 232 1 by 2. So log of square root 16 divided by 232. This will be minus 5. So this will be minus 0. 58. So here by 6 value at omega c1 will be equal to 16 by 32. So this will be square root of 16 divided by 232, and this will be equal to 0.26. Similarly, we can find so at omega is equal to omega c2, so that is equal to 0.2, and that is equal to 1 by 5. So the AR by 6 value at omega c2 can be calculated using this expression. So again we will copy this expression and we will just put here so instead of 1 upon 2 we have 1 upon 5. So we have 1 upon 5, 1 upon 5. So finally we will have minus half log 10, and here we will have 25. So this will be 25 square. So 5 to the power 4. So 5 to the power 4 will be equal to 625. So this will be 625 plus 29 into 25. So 25 into 29 will be 725. So this is 725. So this is 725 and this is 100. So finally we have log 10 of 625 625 plus 725 plus 100. So that is 1450 and to the power half. So this way amplitude ratio by 6 at omega C2 will be equal to So will be equal to 1450 by 625 to the power half minus half, and this will be equal to we'll find out square root of 625 divided by 1450, and that is 0.65. So overall the AR value, AR by 6 at omega C1 and AR by 6 at 0.5 is 0.26, and AR by 6 by at omega C2, AR by 6 at 0.2 equal to 0.65. So using this information we can draw the gain plot. So now continue with the phase plot. So using the phase plot, so now continue with phase plot. So in the phase plot we have to plot phi versus omega, and here we will have 4 different regions. So region 1, when omega tends to 0. So when omega tends to 0, from the expression of phase shift, so from the equation 6 we can copy this. We will put here in this expression. So when omega tends to 0, the phi will be tan inverse 0 plus tan inverse 0. So we will have 0 degree. For region 2, when omega is lies between 0 to omega C2, and this omega C2 is 0.2. So the phi will be tan inverse minus 2 omega C2 plus tan inverse minus 5 omega C2. So now just substitute omega C2 as 0.2 and omega C2 as 0.2 in both the expression. So finally we will have phi will be equal to so here we will have tan inverse minus 0.4 plus tan inverse minus 1, and this will be minus 45 degree. So overall the phi will be equal to minus 66.8 degree. And this will be minus 21, so minus 21.8 degree. So again for region 3, when omega C2 omega is lies between omega C2 and omega C1. So here omega C2 is 0.2, omega C1 is 0.5. In this case we will again copy the phase expression and we will put this omega as omega C1. So when this omega has omega C1, so we will just replace this omega by omega C1. So in this case we will have phi will be equal to tan inverse, so omega C1 is 0.5, so 0.5, so this will be minus 1 plus tan inverse, and this will be minus 2.5. So we will have first will be minus 45 degree and second will be second will be tan inverse 2.5, that will be minus 68.19, minus 68.19. So 5 will be equal to minus 113.19. This is 5 at omega c1. So fourth region 4 when omega is greater than 0.5 and which is again omega c1. So in that case the value of 5 we have to find out. So this will be, so here we will again copy the phase expression and we will put 5 equal to 10 inverse minus infinity plus 10 inverse minus infinity. This is minus 90, this is minus 90. So we have minus 180. So overall 5 will be equal to minus 180 degree when omega is infinity. So overall we have 4 regions. And here we will have nearby 6 and here we will have phase shift. So 4 region when omega tends to 0 and the second is when omega lies between 0 to 0.2 and when omega lies between 0.2 to 0.5 and when omega lies between 0.5 to infinity. So in that case we will have the value of amplitude ratio as well as phi. So let's put the value of phi when omega is 0. So we have 0 degree. When omega lies between 0 to 0.2. So at this higher point at omega, so the phi at 0.2 is equal to minus 66.8. This is minus 66.8 degree, and phi at this point, that is at another corner frequency, equal to minus 113.19 degree. And when phi at when omega tends to infinity, phi at infinity will be minus 180 degree. So we will have these four value of phase shift for these four different regions. And the amplitude ratio when omega tends to infinity, so we have low frequency asymptote, and this value a r by 6 tends to 1. And when omega tends to infinity, so this value tends to r by 6 will have the slope of minus 2. And when the equation of line will be given by the high frequency asymptote line, and that is equal to minus 1 minus 2 omega. So in this case, this log 10 r by 6 is given as minus 1 minus 2 log 10 omega. So this is the equation of high asymptote line. So here the slope is minus 2. When omega lies between 0 to 0.2, so we have the value of ar by 6 at 0.2, and that is equal to 0.26. Similarly, when omega lies between omega c2, that is 0.2, and between 0.5, so the amplitude ratio by 6 at 0.5 is given as 0.65. So using this information we can plot the gain diagram. So now let's plot the gain plot. So here we will have y-axis, this is x-axis. So the y-axis is, the x-axis is omega, and the y-axis is ar by 6. And we know when omega is less than 0, so low frequency asymptote start with a by 6 equal to 1. So this is the equation of low frequency asymptote, and we also know that in this case we have two crossover frequency. One is at 0.2 and the second one is at 0.5, and here this is, let's say, 1 and this is 10, and this is, we have 0.1 and this is 0.01 and this is 0.01, and here we have 0.1. So this is omega C2 and this is omega C1. So we have two corner frequency, one is at 0.1 and the second one is at 0.2. So we can draw two vertical lines passing through these corner frequencies. So for first order system, 1 upon 5 s plus 1. So the tau 1 is 5. So sorry, this is not the corner frequency. So this is 0.1. So this is 0.1 and this is 0.2, and we have corner frequency at 0.2 and at 0.5. So when the first order system is 1 upon 5s plus 1, so the corner frequency is at 1 upon 5, that is 0.2. So this is corner frequency two. So as per the equation, so this is the corner frequency 2 and this is corner frequency 1. And when the another first order system is when the another first order system is 1 upon 2s plus 1. So the corner frequency will be 1 upon 2, that is 0.5. So we have two corner frequency, one at 1 upon 5 and the second one is at 1 upon 2. So for the transfer function 1 upon 5s plus 1, the corner frequency is at 0.2, and in this case the high frequency asymptote, so this first order system will pass through omega c2, and so this will be the high frequency asymptote. So here the slope will be -1, and when omega is equal to omega c2, so the curve will pass through 0.707. So this will pass through somewhere here. So here we will have the corner frequency, the gain plot for first order system 1 upon 5s plus 1, like this, and for the another first order system, the high frequency asymptote will pass through omega c1, and here again we will have the slope of -1. So the line will be parallel to this one. So again the slope will be -1, and it will again pass through 0.707 when omega is equal to 0.5. So in this case the gain plot will be like this. So for the overall case, the gain plot can be plot using this information, right? So when omega equal to 0, here by 6 is equal to 1. When omega is lies between 0 to 0.2, so basically at 0.2 we have 0.65, and at 0.5 we have 0.26. So this is just reverse. So we have to just so this is 0.65, this is 0.26. So at 0.2, 0.6, at 0.5 when omega equal to 0.5 we have AR by 6 is equal to 0.26. So now let's plot the overall gain plot. So here we will have when omega equal to 0, so AR by 6 is equal to 1. So when omega is equal to 0.2, so the value is 0.65. So let's say this is 0.65. So we will just extend this up to 0.2. So at this point this will be the 0.2, 0.65, and when omega is equal to 0.5 we have 0.26, so this will be 0.26. So we will again further extend this up to omega is equal to omega c1, so this will be up to this point. And this way we can plot the overall frequency, overall gain diagram, gain plot, so which will pass through this 0, 0.65, 0.2, and then we will have another. So at this point we will have the slope of, so here the slope will be -2. So this will be the gain plot for this. For the phase plot, again this is omega, this is phi. So when omega omega is equal to 0, so we have 0 degree. When omega is minus infinity, when omega is infinity, so we have minus 180 degree. So these are the two extreme values for lower omega and higher omega. So if we continue extend this omega c2 below in the phase plot, so this will be 0.2, 0.5, and this is 10, and this is, let's say, 1, and this is 0.1, this is 0.01. So when omega is equal to omega c2, that is 0.2. So the value of when omega is equal to 0.2, so the value of phi is -66.8 degree. -66.8 degree. So let's say we have -90 degree in between. So -66 will be somewhere here. This will be -66 degree somewhere here, and this will be the value of phi at omega is equal to 0.2. Similarly, when omega is equal to 0.5, we have phi equal to -100. 30.19. So this is at this point. So let's extend this up to omega is equal to 0.5. So this is this one. So finally we can draw the overall phase plot like this. So which will pass through this and this. So this will be the phase plot for the given system. So this way we can plot individual gain plot as well as individual phase plot, overall gain plot as well as individual phase plot for the complex system. So that's all for today. Thank you.